So let's go into a little bit more detail on activity factor. Keep in mind our power consumption depends greatly on the activity factor of your overall data signals. That's averaging your data and clock and everything all together. So let's go through how we can estimate what our average activity factor is through our logic signals. So first of all, let's define P sub I, or capital P sub I, as the probability that a given node I equals a logic value of 1 on any given cycle. And then of course the inverse of P sub I is going to equal, since probability is a number between 0 and 1, the inverse of P sub I is 1 minus P sub I. And it turns out that our activity factor of a given node I is going to equal inverse of P sub I times P sub I. And that will give us the overall activity factor for a given node. So if we have completely random data such that the probability of any given cycle is 50% probability that it's 1 or 50% probability that it's 0, that means that P sub I is 0.5, inverse of P sub I is 1 minus 0.5, which is also 0.5. So the activity factor is going to be 0.25. And you can figure that out a little bit more just conceptually by saying on a given cycle, if the probability that it's a 1 is 50%, that means if it was a 1 last cycle and then this cycle there's a 50% probability that it's a 1 and 50% that it's a 0, that means you have a 50-50 chance that you're going to switch on the next cycle. So from cycle 0, let's say we're a 1, cycle 1, 50% chance you don't switch, you might stay a 1. And so you've now had 2 cycles in a row where you haven't switched. Then you go to the next cycle, 50% probability that you might go from 1 to 0. Let's say on that cycle it does go to 0, and so you switched on cycle 3, and then cycle 4, 50% probability that you're going to switch again. So every other cycle there's a 50% chance that you switch. And so since you're trying to make a 0 to 1 and then 1 to 0 transition, the full transition from 0 to 1 back to 0 takes on average 4 cycles to happen. And so therefore completely random data, you have an activity factor of 0.25 as your average for completely random data. Now, often data isn't completely random. So for example, in the upper bits of a 64-bit word representing like bank account balances, usually they're always 0 and they'll stay 0 almost all the time. So things like that happen where a lot of data has an even lower probability than random data. And then of course if you have data propagating through AND functions and OR functions, you're going to have a lower activity factor as well, because each data input to a 2-input NAND or AND is activity factor of 0.25. And so if you figure out the AND function, you're going to have even lower than 0.25 coming out when the two activity factors of 0.25 are averaged together. So depends on your design, but typically on average random data through your entire system, it has an activity factor on the factor of about 0.1. So I'm not going to go through every entry in this table, but here we can see how is presented the probability for the output switching based on the input switching for various different types of logical functions. So for example, a AND2, it would be the same for a NAND2 gate. The probability of the AND2 output being high is going to be the probability of the A input being high multiplied by the probability of the B input being high. And so if we have a totally random data signal for both A and B, the probability of either one of them being high is 50% probability. So the probability of the output being high is 0.5 times 0.5, or 0.25 at the output is the probability of the output of the AND2 gate being high. Similarly, for an AND3, you have PA times PB times PC, and so the probability of a 3-input AND gate being the output being high is going to be, for random data coming in at 0.5 each, it's going to be a factor of 1 over 8. 2 times 2 times 2 is going to give a 1 over 8 function. So the other gates, you can see the equations for those. It might be worth printing out this foil or copying down the probabilities for the other functions for an OR function, NAND2, NOR2 function, etc. Let's go through an example of calculating probability and activity factor based on a multi-stage function here. So our example here is we have 4 input, we're trying to do a 4-input, overall 4-input AND function, and we're building it out of 2 levels of logic gates. So in this case, we're doing a NAND followed by a not AND, which is a NOR, and we want to estimate the activity factor, probabilities and activity factors at each of the nodes following the input nodes, and assume that the input data signals A, B, C, and D each have a probability of being high on any given cycle of 0.5, so they're considered to be random data signals. So pause here and figure out the probability and the activity factor of each of the nodes, and then continue on after you've paused. So let's go through. So going through the NAND gate, if you remember, an AND gate had a probability which is PA times PB. A NAND gate, again, this is the probability that we're going to get a 1 out of it, is going to be 1 minus PA times PB. If you go back to the previous foil, you'll see that was the equation for a NAND gate. So the probability is going to be 1 minus 0.5 times 0.5. So that would be 1 minus 1/4. And then our activity factor is going to be the that 3/4 value, because we have 1 minus 1/4, so our probability of being high is going to be 3/4. Our activity factor is going to be 3/4 times 1 minus P, which is 1/4, so 3/4 times 1/4, and we get our probability of being high is 3/4, our activity factor is 3/16, so 3/4 times 1/4. Going on to the output of the next gate, we have our probability of being high is going to be 1/16, and then our activity factor is going to be 1/16 times 1 minus 1/16, or 15/16, and so we get 15 2/56 is our activity factor. And so you can see from that we have a value of, going out of a 4-input AND gate, we get 0.058 approximately. So you can see that depending on the logic you go through, you can start with totally random data, and the activity factor actually gets lower a lot of times as you're going through the combinational logic, depending on exactly what the logic is, depends on how much lower it gets over multiple logical stages. As I already mentioned, one way to reduce power is to try and reduce your activity factor of your average logic. And on the last foil, I showed how activity factor does depend on, as you do and OR functions, you will get lower activity factors in some cases going through the logical ANDing and ORing of different data signals. But it's not something that you can actively change. I mean, your logic is your logic. So you might get lower activity factor on some data signals, but you can't purposely lower the activity factor for a given logical function. So one of the ways that you actually can, and is actually the best way to reduce your activity factor on average, is to pay attention to when your logic is actually being used versus when it's not being used. For example, if you know you have an ALU and you're not sending any function to the ALU, you're not doing an add or a subtract or a multiply or whatever other functions you have, and you can see, possibly even in your pipeline, you can look ahead many different functions and say, oh, I'm not going to use this ALU for 10 cycles. Or if you know you're waiting to receive a request from memory, and you know that that memory request takes 20 cycles to get out to, if you don't have a local memory, but you need to go out to a third level cache or even out to your disk drive or something, you might know you have dozens of cycles possibly. So in those cases, what we do is we can gate the clock to the entire set of logic that we know we're not going to be using for a while. So below here it shows kind of an example of that, where instead of just having a clock come in and go through a number of buffers and go to all of our registers, our flip-flops or latches, we can send the clock into an AND gate and have an enable logic that gets latched just before that AND gate. So we send an enable in. If the enable goes low and then that enable is ANDed with the clock, going forward, anytime the clock toggles, if the enable is low, the output of that AND gate will not be toggling. So none of the downstream registers will toggle, which means none of the logic coming out of those registers are going to toggle, and your activity factor goes to 0 for whatever period of time that you have the clock disabled in effect. So that will lower your average activity factor for all of your logic for however many cycles you aren't using that logic. So this is probably the number one way to reduce your dynamic power consumption, is to use clock gating as much as possible anytime that you know you're not using logic. The next thing on our list as far as reducing dynamic power is, of course, reducing your capacitance. You don't always have the ability to do this, but some ways to reduce your capacitance are, in terms of gate capacitance, potentially using fewer stages of logic. This doesn't always work if, like, let's say you need to drive a really large load. You might need multiple stages of logic in order to buffer up the drive strength in order to get a good drive strength for the last stage that's driving the really large capacitance. But if you have a fairly low capacitance receiver and you're doing a set of logic and you know you don't need to buffer it up, instead of using multiple stages of logic, you might be able to get away with possibly less gate capacitance by using fewer stages of logic if you can optimize it. Just as an example, a lot of times in automated, if you have like an auto place and route or some sort of automation tool to create your logic, sometimes it can throw in extra buffers just because it says, I don't really need to make this logic fast, and there are places where it doesn't optimize for power. It might be optimizing for other things, and throw in extra stages and extra potentially extra gate capacitance. So being able to take out logic that isn't needed, could help your power. And then of course, if you can size your gates smaller, sizing them smaller can reduce your capacitance. And then wire capacitance is something that is a fairly dominant nowadays. Your wire capacitance can be as much as your gate capacitance, depending on the logical function that you're doing. There are designs that are more wire dominated than they are gate dominated, and so if you have that type of design, trying to do good floor planning, keep blocks that have lots of communication, large buses between them, trying to keep those as close together as possible can reduce your wire capacitance. And also, I think I've mentioned this in previous presentations, especially when we were talking about driving long wires. When you're driving long wires, if you do it with inverters where you just have a single NMOS and PMOS, you can make that NMOS and PMOS as small as possible to get whatever drive strength you need, rather than using a complex gate. If you're trying to use complex gates to drive a long wire or large capacitance, they have to be much, much bigger, and so it's not the most efficient in terms of power. Sometimes using a complex gate to then drive an inverter or buffer that drives the large capacitance can be more efficient in terms of power, even if it takes a little bit more delay to go through the gates. And last but not least, definitely not least, as far as trying to reduce your dynamic power, is modifying voltage and frequency. If we can reduce our voltage, like I said before, voltage is a square law effect on your power, so reducing voltage can have a dramatic reduction in your power. But of course, reducing your voltage will reduce the drive strength of your transistors and in effect reduce the maximum frequency that you can operate at. So generally, reducing your voltage requires you to reduce your frequency as well. So of course, you do get a double effect out of that, almost a cube law effect, because you're reducing voltage by a square function, then reducing frequency along with that, and so you can get a pretty dramatic reduction in power. Now, this can be definitely a benefit if you know that the block that you're running, or whatever function that you're running, doesn't need the frequency maybe that some other portion of your circuitry does. So this is a really good technique to use if you have multiple voltage supplies that you can run in different areas of your chip. You can potentially run some areas at a lower voltage and a lower frequency if they're not as critical to your performance. And so that's one key way in a lot of modern IC designs, is using multi-voltage domains and even multi-frequency domains, and just having each domain at the level of voltage and frequency that's needed for the performance that you need as an overall chip. Now, two of the problems that you have due to having multi-voltage domains and multi-frequency domains, one is for voltage domains, if you need to send signals between two different domains that are at different voltage, you actually have problems with a lower voltage signal trying to drive into a higher voltage domain in particular. And so you need level converters or level shifters in order to get the voltage up to the full value of the receiving domain when you're coming from a domain that's at a lower voltage. So you do need to keep in mind that every signal that crosses voltage domains, you might need these level shifters, and potentially even another circuit device that's called an isolation device, where if one voltage domain actually goes down to zero, like if you disable that voltage domain because you know you're not going to need any of the logic that's in that domain isn't being used at a given period of time, you might want to turn off the voltage completely. to eliminate both dynamic power and static power through leakage. And so when you do that, you want to make sure any signals coming from that domain have some sort of default as they're going into a domain that has power. If you're coming in from a domain that doesn't have power, you can run into problems, and so you have to have something that detects that and says default to a 1 or default to a 0 when the power domain that this signal is coming from gets turned off. So there's level converters and there's isolation devices to do that. And then if you're the other thing that you can do is, instead of just having voltage domains that are at different values than each other, you can dynamically adjust your voltage in a given domain. So maybe you might have it at 0.8 volts at a period of time where you're doing something that doesn't demand a lot of performance, and then have it ramp up to 1 volt or 1.1 or 1.2 volts at a time when you know you need extra power or extra performance coming out of it. So that's called dynamic voltage scaling, where you can adjust your voltage and your frequency depending on some critical workload that comes in.